Boom. Hello and welcome back to Calculus 1 after this long and dreaded weekend, right? Finally back in Calc class and you can enjoy for next 2 hours. Let me see those smiles. I guess rain, right? Anyway, the lesson is on linearization and differentials. Some of this is a bit irrelevant today due to our computing power, meaning calculators, computers, and so on. The methods are still used in very advanced mathematics, but on the level of engineering, you just take the calculator and you compute ln of 3 if you need to know how much ln of 3 is. So both of these methods deal with calculating values, approximating values, function values. And the first one, linearization, is linked to the problem of the tangent line, which is actually what we are doing. We're just giving it a little bit different name. So, saying that you are interested in, let's say, square root of 10. You want to compute square root of 10. You know that the function in which you would be plugging numbers to deal with is square root of x, whose graph looks like this, right? Now, somewhere over here is the number 10 that you are interested in. You are interested in a y value because this question mark here is the y value for that calculation. But the trick is that for these well-behaved functions, you can find the tangent line at the point that you know how to take the square root of and put the tangent line there. Now, when you do that, you see that the tangent line passes very close to the point in question. And this particular graph, it's kind of looks like it's going through the same point. It doesn't. So this red line has the equation y equals mx plus b, where this m is the derivative computed at 9. And the black line is the square root of x. So now I'm going to say that I can approximate square root of 10 by calculating the m times 10 plus b, right? So that's the idea. That's what we're doing. So if I am able to find the tangent line close to the position of the number that I actually want to calculate, I will be able to calculate roughly the value of that number, because the y values are nearly the same. The y value from the red line and the y value from the black line are almost the same. They're not the same, but they're almost the same. It's close enough. So let's see how this looks like. We know how to find the tangent line for f of x equals root x at a equals to 9. To find the tangent line, we find the derivative, right? There we go. So the first derivative would be 1 over 2 root x, which means that the slope is 1 over 2 root 9, which in this case is 1 over 6. We also have the point 9, 3, right? Because x value is 9, which we know, and we can calculate square root of 9 is 3, so we have x and a y. And now when you plug that in into y equal mx plus b, you have your y as 3, you have your m as 1 over 6, you have your x as 9, and you just need to figure out b. So now this is 3 halves, so b is equal to 3 minus 3 halves, which is 3 halves. And we have the tangent line y equals 1 over 6x plus 3 halves. So what I'm claiming is that the square root of 10 is approximately equal to 1 over 6 times 10 plus 3 halves. Now, something like this you can actually do without the calculator. Yes?
Can you narrow it down even further by using a tangent line just before and just after?
But yes, but the problem is that we can't take the square roots. That's why we're doing this, right? 9 is the nice place where we take the square root. The closer you are, the better. Right? So we could have done this at 4, but 9 is much closer. We would have done it at 16, but 9 is much closer. So 9 is the closest spot to 10 where you can compute your function nicely. Then we'll do other examples with other functions and so on, so it gets. But yes, you are correct. The closer you are to the point of interest is more precise. So 10 divided by 6 is 5/3, right? Plus 3 halves. Oh, actually, I don't know why I did this, because the common denominator is 6. So I can just do that. So it's 10 plus 9 over 6, 19 over 6. So what I'm claiming is that the square root of 10 is approximately 19 over 6. Now you can use your calculator to verify that these two values are indeed extremely close. So you first find the square root of 10. Just to verify things. So the square root of 10, calculator says, is 3.1622776602. That's what the calculator gives me. And 19 divided by 6 is 3.1, and then 6 is forever. Look where it's off. 4/10 of a cent. You don't need this precision even to build an engine for a car. Right? Tolerances for engine for a car are bigger than this. So we are talking about instant great precision right away. Let's see another example. And what am I doing? I'm looking for the tangent line at the point closest to the point of interest, and I'm computing the point of interest in that tangent line rather than original function. So let's say you're out with your friends, ln of 3 comes up, you can brag that you are the only person who can compute it by hand. And probably everyone else will be just staring because they won't know. So how much is ln of 3? Yeah, we can be lame, take the calculator. Yeah. Let's actually do it. Which number that it's easy to compute is close to 3? E is about 2.7, right? 2.718, right? So on. So E is close to 3. Now someone will say, well, what if I have to do 5? You still use E. What if I have to use 10? Use E squared, right? Because E squared can be computed. Obviously, ln of 1 is 0, so there are certain values in incremental powers of E that you can compute easily. E to any power you can compute very quickly. E to the 7 halves. It's fine. because 7/2 jumps in front. Ln of e is 1, so it's just 7/2. Anyway, e is close to e, so we are looking for the tangent line of f of x equals ln x at x equals e. And we run this calculation. We don't need calculator for this. That's what's the awesome part. So what's happening here? Tangent line. We know what to do. Find the first derivative. That's how we find the tangent line. Find the first derivative, which for ln x is 1 over x. And then slope is immediately 1 over e. So there's our slope, 1 over e. And we have the point e comma 1, because when you plug e back into ln, ln of e is 1. So we have x comma y. So now I have y equal mx plus b. Plug in y, which is 1. Plug in m, which is 1 over e. Plug in x, which is e. And then plus b. We see that b is 0, right? Because e is cancelled, 1 equals 1. So b is 0. What is the tangent line? Y equals 1 over e x times x. So how much is ln 3? ln 3 is going to be approximated by calculating 1 over e times 3. So that's 3 over e. E is about 2.7. This is approximation anyway. So we have 3 over 2.7. Well, that's approximation, so I'll have to put another squiggle there. Yeah, now you can multiply top and bottom by 10 to get 30 over 27. Cancel it by 3. Get 10 over 9, which gives you 1.11111 forever. So we are approximating ln 3 as 1.11111 forever. Yes?
So specifically 1.103.
What, 10 divided by 9?
No. Divided by e.
Yeah, but see, what we're doing here is we are not using calculator at all. Now you're going to tell me ln 3 calculator value. Hold on, comrade. 0.98611
or 122.
89. There we go. Now look where it's off. It's off 1 cent. That's how much is off. We didn't use calculator anywhere, right? You can use the stick in the sand, right? You know all the story, right? Desert island, right? The battery in the calculator is dead. The battery in the cell phone is dead. Wilson is gone. You have nothing else to do. Stick, sand, math, ln3 by hand. You are recreating mathematics so that you can remake all the physics and engineering and everything so you can build stuff, right? So I'm going to challenge you guys with a question. How much is cosine of 3? So what's A? First of all, what's the function that you're looking at? Cosine x. And what's A? Pi. Nice. 3.14, right? Now remember, any other number is going to have some kind of deal with pi. Pi over 4, pi over 6, pi over 2, 3 pi, and pi, right? Any number that you come up with, you will be able to do it. All right, let's go. But then you can't stand them, right? Head drop. If there's room, there's no overload. Doesn't matter.
Look familiar? What if the teacher just like wrote on the board all of you failed students semester?
That'd be even better. I thought we had only the agreement what was said in class.
No. We can bend the rules a little bit.
Oh wait, no, this is other room. I'm done. 21 more spaces.
You can switch right now.
I already paid my class.
I mean,
Doesn't matter.
I didn't.
It's the number of credits, not which class. You can switch your DPQ for English 1. It's the same price. 3 credits is a big credit. But you know, what? No.
The thing that I was about, the thing that it opened up.
Actually, no, I snagged a spot. There was one opening.
Sometimes students, when after some time, they move or something. But there is always a wait list and all that stuff.
No pressure.
Has no quiz because there's no more error. So all right, do we all have this done? What is the value? 0.99999? All right, let's take a look. So the function is cosine x. A is pi because that's 3.14, close to 3. And then we have the tangent line. So the first derivative of cosine is negative sine x. And we are calculating the this at pi, negative sine, so So m equals to what? Negative sign of pi, which is 0. So the only thing that we can do here is, as we are calculating, right, a is pi, so y value is cosine of pi, which is -1. So we have the point to be pi -1 and m to be 0. That's just then -1. What happened? So what's the tangent line? Y equal mx plus b. Y is -1, m is 0, x is pi, plus b. B is -1, so y is equal to -1. This is the line. That's the line. So we are claiming that the cosine of 3 is approximately -1. Now your calculator better be in radians if you want to check this. And you type in, right? So what do we have? For cosine of 3, what do you get? In a calculator. -0.9 what? I see how it is.
I got negative 0.989992496.
When you round this 8 to a 9, you are again 1 cent away. See, these methods are very, very precise. They're approximation, they're not exact, but they're good enough. You're able to find any square root, any ln, anything, using these methods. So now what I'm going to write is a formula which takes the entire procedure for tangent line and writes it in a one-line formula. And that formula is L of x is equal to f of a plus f prime of a times x minus a. This is known as linearization, but it's actually a tangent line. It is a tangent line. So if you are trying to figure out where this thing comes from, I will remind you of the formula that you learned in algebra. Y minus y1 is equal to mx minus x1. I will also remind you that f of a is a pair, which in this case is x1, and f of x1, which is known as y1. So when you plug all of these things in and move y1 to the other side, you'll see that this is just your algebra formula, written to the calculus language, where the slope is calculated through the derivative. So that's all it is. It's nothing special. You are going to expand greatly on this in Calculus 2. Those of you going to Calc 2, you are going to see something called Taylor polynomials, and you guys are going to add infinitely many terms to this later on. So this is linearization. And I wanted to work out an example from the textbook. Well, we'll ask you to work out an example on the textbook using linearization formula. So let's find something cool. All right. Ready? So I want you to plug everything in the formula and compute from there rather than computing pieces. So problem 16 gives you the function x over x plus 1. And they want to know how much is f of 1.1. So what is your a? 1. All right, go. Compute the formula for this.
Yeah, we're gonna do the root ratio comparisons and the alternating. Finish that way. Because it was too much fun, right?
Yes. Trying to get the test that they work.
Let's take a look. So when you look at the features, f of a is going to be just the function computed at 1. F prime of a is the derivative computed at 1. X is going to be 1.1 and a is 1. So we plug everything. Well, first we find the derivative. If you want to use the quotient rule, all right, that will be the quotient rule. Take the bottom derivative of the top minus the top derivative of the bottom. Good. And when you simplify this, it works out to be 1 over x plus 1 squared. So now, how much is the linearization for 1.1? Right, what's the formula? Its original function computed at 1, so 1 over 1 plus 1, plus the derivative computed at 1, which is 1 over 1 plus 1 squared, times x, which is 1.1 minus a, which is 1. So this is your x is 1.1. So you just plug in, and we get 1/2 plus 1/4 times 0.1, which is 1/10. So you have 1/2 plus 1 over 40, and then that's 21 over 40 altogether. So f of 1.1 is approximately 21 over 40. Now it looks like overkill, right? It was easier to just compute 1.1 in the original function. But remember, this is not done for such a simple problems. Equations in engineering are much harder than this. Yes?
So that's the same answer we would get for y.
Yep. If you do the tangent line procedure, you will have to get the same. The second part of this lecture is differentials. First, I'm going to write that differentials approximate the change in value, not the value. So let me actually write linearization approximates the value. Differentials approximate the change.
When you say change, you mean the change between the approximation and the actual value?
No, the change in value as input goes from one number to another. So I'll give you the example. Here is the area of the circle formula. And let's say the circle becomes larger. Remember how we had the oil rig, and the oil rig was spilling the oil around in a concentric circle, was growing? So we are not going to calculate the rates here. I want to know when I use input R1, I get the output A1. When I use R2, I get A2. When I use R3, I get A3. But what I'm looking for is the change in area, which is A2 minus A1. That's known as change in area. So the new one minus the old one. It's delta A. So you see that R changed. There is a delta R involved, which is R2 minus R1. So what I want to use differentials for is to approximate this change. That's what I'm trying to figure out. So what kind of change? Delta Y change. That's what I'm approximating. Now let's derive the formula quickly. It's 2 lines. you know that you write y equals f of x. You differentiate both sides. One side you write as a Leibniz notation, the other side is the modified Newton notation, and then you ship dx to the other side. Now, this is extremely important. Delta x and dx are the same thing. Delta y is approximated by dy. They're not the same. So this formula here is differentials. Very simple to use. So let's say you have a triangle with a height h and a base b. Let's say that the height is constant and the base b goes from 3 to 3.1. And height is constant always, let's say 5. Approximate the change in area. You have to have a motion, guys. Something has to change in order to, so input variable has to change in order for the output, for the dependent variable to change. In this case, area. So we know the area of the triangle is 1/2 base times the height. In this case, height is always constant, so it's 5/2 b. If I figure out the derivative, right, because b is the variable, independent variable, I will be taking the derivative in respect to b. So what I have on this side is dA dB is equal to 5/2, and then I move dB to the other side, and I have my differential. Now observe that this dB is the same as delta B, and delta B is 3.1 minus 3, which is 0.1. So the change in area is approximated by dA, which is equal to 5/2 times 0.1, which is 5/2 times 1/10. These guys cancel, and you get a quarter. So we are approximating that with the base growing 0.1 unit, the area will grow quarter of the unit squared to accommodate for that growth. You can calculate exact, but exact takes a lot more computation, and mainly might use the calculator, right? Because the state 1 was when you had the area to be 1/2 base, which was 3 times 5. So you are working with 15/2. State 2 is 1/2 of 3.1 times 5. Now you see that there's this 3.1, and now we have to calculate with that. So that's 15.5 divided by 2. And now when you subtract these two, we get that the delta A is actually 1/2. Well, this is approximation, so it's not exact, but for many applications, good enough. we can use it to still calculate all of the previous problems that we did with the line up there, with the linearization. You remember the ln3 problem? We can actually compute ln e plus the change in y will approximate ln 3. See, I need to, what we say, perturb, right? We need to change a little bit ln e. ln e is easy to compute, so I just need to add a little bit. So my goal is to figure out how much is that dy that I need to add. Now we know that that dy is the derivative times dx. So the derivative is 1 over x and times dx. So we are recognizing this calculation here now because that's the derivative and that's the dx part, which is the delta x part. So now how much is my delta x? Delta x is the e minus 3. So dy is 1 over x, which is 1 over e, times e minus 3, which is e minus 3 over e, which is 1 minus 3 over e, if you want to keep the exact values. So how much is ln 3? ln 3 is approximated by ln of e plus 1 minus 3 over e. ln of e is 1, plus 1 is 2, so 2 minus 3 over e. How much is 3 over e? It's about, we know that from earlier, 1, 1, 1, right? So this is equal to 2 minus 1.1111, actually approximated, not equal to. And there's your ln 3 answer. So we can calculate the values with this, but we can do a lot of very important engineering. Guys, you know when you are on the train and you hear the tuck-tuck, tuck-tuck sound all the time? What happened? Split second. You asked a split second.
Like 7.
All right. So you guys know when you're on a train, if you ever take the train and you hear the tuck, 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 tuck. Why is it there? What is that sound? They need to fix every train that exists on the planet, or what's the deal? The deal with that is the tracks. The tracks have to have gaps because the tracks are long and we have something called summer. And what happens in the summer? They heat up and they expand. So when you have two tracks, and if you don't leave the gap in between, when they expand in the summer, they will push against it, and then the forces will put them apart, and everything falls apart. When you're driving over larger bridges, you've seen those parts that lock together. They lock together in the summer. So you drive over a bridge, right? It's a lane. And there's this zigzag thing in a bridge. That's where the bridge is actually broken on purpose. In the summer, they lock in. In the winter, they go apart. They don't go apart enough for your car to fall through. They go apart a few inches. But if that wasn't there in the summer, those few inches of lead time, right, would lock in and the bridge would fall apart. So next time when you are on one of the big bridges, as you're driving, you will see these things. You will drive over them, right? A lot of design has to use this concept of heat actually expanding objects. As engineers, you have to predict that. I also mention every time the design and the CD discs, then I realize that you don't know what that is, then I switch to DVD, then I realize that you don't know what that is, so I'm finally down to Blu-ray, all right? So when you're looking at the Blu-ray disc, right, the Blu-ray disc spins, and you have what? What reads the Blu-ray disc? A laser. And what the lasers do? They heat up stuff, right? So the laser is on this linear track going left and right, where the disk spins with some omega speed, and information on a disk starts in the middle and it spirals out. So when the disk is hot, it expands, and if that expansion through differentials and stuff is not incorporated in the programming that leads the laser, it would read different type of data for the different temperatures. So you read the disk, let's say in the summer in a car, and you read it in a house, and it's going to give you, it's going to play normally in the house, and you go in a car, it's going to do, right? Because it will not be reading data correctly. So you have to incorporate the expansion. Now you would say, well, that is not that much. It's enough for the laser precision read, right? It's not enough for you or the LPs, right? But for something that is laser precision for reading, you have to compute these things. You have to take it in consideration. So there is a lot of engineering applications for this session. Let's take a look at some of the word problems they have in the textbook that pertain to differential. Well, first let's do a vanilla problem. So they want you to unleash the differential upon problem 50. It says f of x is equal to ln of 1 minus x. They just want you to set up the formula for it. I don't think you can get easier problem than that one. Yep. So dy is equal to, the derivative of this is negative 1 over 1 minus x dx. So dy is equal to 1 over x minus 1 dx. So what I did is I applied that negative, and then that switches the signs in denominator. That's it, right? So now, if x grows from, let's say, 3 to 3.2, you plug in 3 and then 0.2, and you compute the change in y. But let's take a look at whatever here, 36, a word problem. It says approximate the change in the volume of a sphere, approximate the change in the atmospheric pressure when the altitude increases from z 2 kilometers to 2.01 kilometers. Why is this relevant? Airplane design, very good. Airplane design, rocket design, all of this stuff. So the function for change in pressure in respect to height is 1000 e to the negative z over 10. Z changes from 2 to 2.01 kilometers, and they want to know what's the change in pressure. So they want to know dP, which approximates the change of pressure. Go. Negative c over 10, otherwise c. Height. 3D.
What unit is that?
Kilometers.
No, I mean pressure.
Oh, pascals. So we start by figuring out the derivative. So we have a dP dz, copy 1000, and then e to the negative z over 10 times the derivative of the top, which is negative 1 over 10, which gives us the derivative of negative 100 e to the negative z over 10. So dP is equal to negative 100 e to the negative z over 10 times dz. Now dz is 2.01 minus 2, so we plug that in, and the change in pressure is approximated by dP, which is negative 100 e to the negative 2 over 10. Right, we are plugging in 2 now. Negative 2 over 10 times, this is 0.1. So the change in pressure is approximated by dP, which is negative 100 e to the negative 1/5, and this is 1 over 100, which would cancel. So the whole thing is just negative 1 over the 5th root of e. That's what it is. Like 1/5 is the 5th root, negative pushes it downstairs. So you can compute this value.
Where did the negative 1/10 come from? 1/10.
Oh, the chain rule for the chain rule for the exponent. And now you can see that we are getting less pressure.
Where did the 1 come from?
What happened?
If that's chain rule, where did the 1 come from?
Because it was derivative of z is 1. So negative z is negative 1 over 10. If there was no z there, it would be a 0 in a chain rule because it will be constant. I'm getting negative 0.8182. Yep. Good.
Yeah, as far as either one is about, I think, 6 milligrams of mercury, which is, that's ridiculous in terms of pressure.
Yeah, but we're only moving 10 meters.
I know, but
10 meters is 5 times my
I
height.
don't know
No.
what normal pressure is supposed to be at 2 kilometers above sea level, but I doubt it's 6 milligrams of mercury. That's normal is 760.
Maybe different units? I don't know. Didn't say anything. Or maybe it's in atmospheres. 1 atmosphere is pressure on the air, so maybe.
800 atmospheres.
No, this is the change in atmosphere, so we are losing 0.18 of an atmosphere. Maybe too much. All right, that's that. Let's take a break and then mean value theorem when we resume.
That 4.6.